For our example, we will be making smoothies. Every smoothie will have 1 cup of plain yogurt, 1 secret ingredient, and a bunch of random food dye so that you cannot tell what is in there. I blend it up, I serve it to you, and your goal now is to shout at me, what are the calories in this smoothie? Go. What do I hear?
100.
100. Going once, going twice. 300. 500. Now, I'm doing a little test here. Seeing who's got the strongest aptitude in the audience for machine learning. Because the machine learning attitude is not the attitude of perfectionism, of think carefully and get the answer right on the first go and don't even try it unless it's going to be perfect. No, the attitude is go for it, see what happens, get it wrong, because you're going to have to do it over and over again. You're going to fail, fall down over and over again, pick yourself up, try again until finally it works. And you have to try something to know what to do next. And so if you're too afraid to start, you tend not to do well in applied machine learning. So those of you who are brave enough to just go for it even though you didn't know the right answer, yeah, that was what's going to get me to move to the next slide and give you more information, and we'll be able to iterate towards correct together. Okay, so you've unlocked the next slide. Turns out this was, what was the secret ingredient? 58 delicious grams of sardines with 265 calories in there. Lovely. I see you don't want to drink it. Fine, I make you a different one. Guess the calories now. 80, 400. 180. All right, I'm hearing some more responses and rumblings. Now let me tell you what was in here. 50 grams of not delicious waffles that I've shown you in the picture. No, the raw stuff, waffle mix. And this is actually an homage to a standard hazing experience that happens on the 5th floor of the Google office here in New York, which is most new Googlers, myself included, I've done this. You walk up and you see this delicious smoothie and you try it and it is not a smoothie. So standard newbie hazing experience here. Okay, so you don't want to drink this one, fine, I make you a third one, but before I make you guess, I'm going to give you a little more information. This is the 16th smoothie that I've made, and here are the 15 previous calorie amounts. Your first reaction to this should be not trying to read it, but instead stamping your foot and saying, I'm a human. I don't add numbers up. That's what machines are for. Indeed, correct. So the machine's going to help us out and summarize them. And we find out that the average is 237 and the middle thing is 240. Have a guess now as to the calories of this one. 237 I'm hearing, 238, 240. Notice how your range has narrowed a whole lot as I give you more information. That's going to be key to our discussion. Okay, I'll go for 237. It turns out to be 88 grams of quiche Lorraine, clocking in at a whopping 445 calories and proving to us that any liquid diet is beatable. So how did we do? We had an underestimate of 208 calories with that strategy. And can we do better? Well, maybe it would help to have the weight of the secret ingredient. So what we'll do as analysts is we'll make a little plot, and we'll have the weight from 0 to 200 grams on the x-axis and calories from 0 to 500 on the y-axis. And as we look at this, we ask ourselves, is there anything going on, or is weight completely useless here? What do you say, completely useless? Something to it. And since there's something to it, maybe we'll go ahead and we'll try it out, shall we? And regression is about putting lines through stuff, so why don't we put a line through it? You like that line? Good line? We missed. Where should we put this line? By the way, those who forgot how lines work, here's a handy cheat sheet. The recipe, the model, is simply intercept plus slope times the weight. So we'll have two numbers here in red that we have to find or discover that determine where the line goes, and then we pop the weight in there and read the calories off of it. So that's what we're dealing with, straightforward stuff. So You don't like my line? Okay, fair enough. How about that one? You don't like that one? This one? It's a tough crowd. That one? No. This one? You look offended. Why do you look offended by this? Because let me remind you of something real quick. This right here, this is your previous model. And now you're offended. But before, you were very happy to just guess 237 every time. 237 and 0 times the weight means I ignore the weight and say 237 every time. And you were so fine to use it then. Check your feature engineering privilege. What is feature engineering? That's when we create inputs that we might use to learn from. Stuff that might inform our solution. And when we have a feature that we might use, suddenly we can do better. So that's kind of going to be the point here. As we get information that's going to be relevant to solving this thing, we expect to do better and better, and it's going to be up to us to think about what information might be worth putting into the system in the first place. Okay, so let's do better. If we can do better, we're going to find a line that's as close to the points as possible, because you seemed offended when I wasn't doing that. Fine. So we better define a notion of an error. What's an error? It's just the point minus the line, the truth minus what we were saying we should predict. And because we all have type A personalities here, we hate errors. So we are going to minimize a function of these errors. That is going to be the score for how this thing performs. And a good score is to have fewer errors, and we will use the RMSE here. And this thing is very creatively named. It's actually the recipe for calculating it backwards. Get the error, square the error, take the mean or average, and take the square root of that. Root mean squared error, or RMSE. Okay. Or you could just think of the RMSE as the calories we're off by on average. Not technically correct, but good enough for government work. We're off by about 85 calories on average, and that'll do. That'll fine for a morning. So now we're off by 85, and we want to be off by fewer. So let's see if we can just jiggle those two parameters there in the recipe to make things better. What do you want to do? Maybe you want to increase the slope a bit. Okay, that's getting better. Good. How about we increase the slope a little more? Not so much better. Maybe now we want to move the intercept down, so let's do that. And what we could do is we could continue tinkering with these two numbers, with slow, boring tinkering, or we could get on with it. So what are our options? Just play by hand with those two numbers, which is what we were doing, or we could use calculus, but who even does calculus anymore, so old school. Or we could just use an optimization algorithm to get us the answer immediately. So what does an optimization algorithm do? It says, for this setting, you are trying, what's your goal? You are trying to get this function right here to be as low as possible. Let me figure out for you what settings on those two parameters that I'm allowed to play with give me the best possible performance here. And then it outputs you that answer. And that's going to be in the heart of every machine learning algorithm. So we're going to need to know what the scoring is, what the goal is, and then it's going to figure out where to set the free parameters in the recipe based on that. Okay, great. And we have come a long way. I'm impressed with us. Nice. Let's look at Quiche-Lorraine, though. It's taunting us. We did not predict Quiche-Lorraine well. How did we do? Better. Our underestimate has gone down. Okay. Can we do even better?